class today, we started talking about first-order linear equations. In particular, we looked at an example of a non-homogeneous equation in which we could write this general solution as a combination of a particular solution, which we obtained via guess and check, and a solution to a complementary homogeneous equation. The example from class today is a demonstration of what I like to call the fundamental theorem of Math 57. The fundamental theorem of Math 57 states that the general solution to a non-homogeneous linear first-order equation, which we already recall can be written in the generic form y prime plus p of ty equals g of t, is a sum of a particular solution and a complementary solution. So yp is any particular solution to the given dE, that given non-homogeneous equation. We'll be talking in this video about a better way to guess that solution than what we did in class. The y sub t is always easy to find by direct analytic methods, in fact separation of variables, because y of c of t is the solution to the complementary differential equation, which is the one we obtained by zeroing out g in our original dE. The fundamental theorem of Math 57 is really a special case of the principle of superposition. You may encounter this, or may even have already encountered this, in classes like circuits, electricity and magnetism, or other engineering and physics courses. The principle of superposition is a broad-reaching principle that applies to any linear system. Pictorially, you can think of this principle as saying that if I have two separate inputs, G1 and G2, and I want to understand the system, how the system would respond to a combination of those two inputs, all I need to do is start by understanding the individual contributions, the outputs that I would obtain from each of the inputs G1 and G2 taken by themselves, and then simply add those together to get the combined output of those inputs. Seems really simple, right? Unfortunately, it actually fails for many nonlinear systems, and we'll see that later in this class. For now, in the case of first-order equations, what the principle of superposition says is that if I have one solution to a linear equation with forcing term g1 of t, and I have a second solution to the same equation but with a different forcing g2 of t, then I can add my two solutions y1 and y2, and this is going to be a solution to the equation y prime plus p of ty equals g1 of t plus g2 of t. Now, to see how this is connected with the fundamental theorem of Math 57, let's take a special case where my g1 of t is the forcing of interest in our particular problem, and our g2 of t is just 0. In that situation, you can see that the first solution, y1, from my example above, would correspond to the particular solution that we drove via guess and check, and the second solution would correspond to a complementary solution, a solution to the complementary equation. So adding those together by the principle of superposition does give me a solution to the full non-homogeneous equation. That's all well and good, but you're probably asking yourself at this point, right, how do I use this in a specific example? Let's go back to our earlier case where we solved the equation y prime equals t minus y with initial conditions y of 0 equals 1. In that situation, we saw in class that a particular solution to the equation can be given by yp of t equals t minus 1. Similarly, the complementary equation, the one we get by getting rid of the forcing, well, I think the easiest way to see that is to rewrite our original equation with all y terms on one side and everything that only involves t on the other. If we do so, then whatever is on this side of the equation is our g. And to convert to a complementary equation, we would get rid of the forcing and rewrite the equation using only what's left on the left-hand side. Now, this equation is extremely simple. In fact, it's one of the ones we solved on the first day of class. Via separation of variables, we obtain the general solution y of t equals c e to the negative t. And just to make this a little less cumbersome to look at, let me erase that mess up and write it in a more proper fashion. Now, once you have these two solutions, the complementary solution and the particular solution to the equation, we add them to get a general solution to our original equation. Yp of t plus yc of t equals t minus 1 plus ce to the negative t. And the advantage of doing this is now I can calibrate my solution. I can choose a value for this unknown parameter c, which will meet the initial condition. So, plugging our statics in, or plugging shit in, depending how you like to interpret PSI, we set 1 equal to y of 0. When we plug in 0 into our formula for y here, we would get 0 minus 1 plus ce to the negative 0. And if we solve for c in this scenario, we get c equals 2, which means our solution to the given initial value problem is y of t equals t minus 1 plus 2e to the negative t. This example was hopefully fairly simple to follow, but you might guess that the most complicated part of using this fundamental theorem to solve non-homogeneous equations is in trying to guess the particular solution. To work towards a better way of guessing the particular solution, let's look back on the two examples of non-homogeneous linear equations which we've encountered thus far. In the example from the previous slide, our forcing function g was a simple linear function of time, and notice that our particular solution also turned out to be linear but with different coefficients. Similarly, when our forcing function was sinusoidal in nature, as demonstrated in the graph from our lab yesterday, the output, y of t, the solution to our differential equation, also tended to have a sinusoidal feature to it, even if it might have had a different midline, a phase shift, and a different amplitude than our input. So this idea that the form of our particular solutions or our outputs should in some sense match our inputs is the basic idea behind the method of undetermined coefficients, or muck, as I like to stylize it after a mispronunciation of one of my favorite Pokemon characters, or a misspelling at least. So the idea behind the method of undetermined coefficients is that if we're given a specific forcing function g of t, we're going to choose a trial solution yp of t from that same family of functions, but with potentially different coefficients. So to demonstrate, let's suppose, like in our last example, that our forcing g of t was just t. Well, this comes from a linear family of functions, so we're going to choose a trial solution, which is a generic function chosen from that family. These coefficients here, big A and big B as I've labeled them, are what we call undetermined coefficients, and are the reason for the name of this method. It doesn't matter so much that you use big A or big B or M or little b, whatever you're most comfortable with. I'm going to try and stick to capital letters here just for consistency. As a second example, let's suppose instead that our forcing function was sinusoidal, as in that last example. Well, in this case, the family of functions here, which we want to draw from, and this is where you have to be a little bit careful and it might not be obvious at first, but the family of functions we want to draw from would be allowing for the midline to vary. As we saw, we got a different midline in the graph on the previous page. Allowing the amplitude of the sine part of our wave to vary, but also allowing for a cosine term in our expression. And the reason for this cosine term is because we saw a phase shift, and phase shifts usually occur when you have combinations of sines and cosines of the same frequency. The third example we're going to encounter in this section is when our forcing term is an exponential. Let's say e to the negative t. In that case, we would choose as our trial solution a particular from that same family, but with a coefficient that's allowed to vary. Same exponent, but varying coefficient. To demonstrate, in this video, we're going to look at two examples. First, we're going to look back at the example we've already completed because it's a fairly simple one to complete. I also would recommend that when you're working with undetermined coefficients, it's useful rewriting your differential equation in kind of the standard linear format with all the y terms on one side and the t terms on the other before beginning. Now, if I want to use the method of undetermined coefficients to approach this problem, the first step would be to identify the family of functions for g. In this case, g comes from a linear family, as mentioned on the previous slide. Therefore, if I'm choosing a trial solution to this equation, I'm going to choose a generic member of the linear family of functions, a times t plus b. Now our goal, you always keep in mind, is to solve for big A and big B. So to figure out the right values, we're going to go back and we're going to plug in our trial solution into our dE for y and figure out the values of A and B, which give us an equality in the equation. So if I plug in AT plus B here, that means I'm going to have to differentiate that expression. If I plug it in here, that means I do nothing to this expression. But at the end, I should get t. The derivative of AT plus B is A. So I end up with an expression that big A plus big AT plus big B should equal t. At this stage, you might be wondering what's going on here. There's three variables, t, a, and b. But remember, what we're trying to do is make this function look like this function, which I should really think of as t plus 0 for consistency of form. So on the left side of the equation, if I look at the constant terms, notice that I have two of them. I have a plus b, and that sum of those two terms needs to be equal to 0 for these two sides of the equation to be consistent. I also need the coefficient of t on both sides of the equations to match, which means that a has to be equal to 1, which is the coefficient of t on the right. Solving these equations for a and b, we see that a has to be 1 and b has to be negative 1. So when we plug back into our trial solution, we get that yp of t should be a times t plus b, which is t minus 1 as achieved before. To demonstrate muck with a slightly more computationally involved example, let's return to the mixing problem from yesterday's lab. In this problem, we were trying to solve the differential equation y prime equals 2 plus 2 sine 2t minus 2y with initial conditions y of 0 equals 0. You might also recall that our forcing function in that example, g of t, had a very specific meaning. It was an input into this reservoir, and the y, our solution, was actually the output of chemical on the other side. So this sort of example is a good one for demonstrating how solutions to non-homogeneous problems help you get at this input-output kind of relationship, which we'll be exploring as we proceed further into the course. For the purposes of solving this initial value problem, though, the first step would be to rewrite in standard form and to recognize at this point that our forcing function g is a sinusoidal. So I can choose my trial solution to be an arbitrary member of that family, yp of t equals a plus b sine 2t plus c cos t. And remember, our goal then is going to be to solve for a, b, and c. If you're still feeling a little bit iffy about the addition of this final cosine term into the expression, try doing this next part of the problem without it and see what happens. With all that being said, we're going to plug this trial solution into our differential equation and solve for those three unknowns, a, b, and c. Recall that when I say plug into our dE, what I mean is that everywhere where I see y in the differential equation, I'm going to replace it with yp of t, which means if my differential equation says to differentiate y, I'm going to have to differentiate all three terms in yp of t as well. And if my differential equation says to multiply y by 2, then I'm going to have to multiply each term in this equation by 2 as well. The derivative of yp prime is 0 plus 2b cosine 2t minus 2c sine 2t. And if that's confusing to you, you may want to think about going back and reviewing some more Calc 1 before proceeding. When all the smoke clears, I'd like to be able to add to this 2 times yp of t, as my differential equation specifies I should do, and end up with 2 plus 2 sine 2t on the right-hand side of the equation. So what we want to do, similar to our polynomial example, is match like terms. The first type of term I see appearing on the left side of the equation are constants. I have a 0 here, and after I multiply things out, I have a 2 times a here. So if I match up the constants on the left with the only constant on the right, we can see that we obtain a simple equation which we can solve for a and get 1. The next type of term I have on the left are my sine terms. I have a negative 2c times sine 2t here, and when I multiply out, I get a 2b sine 2t here. Combining these coefficients, we should have 2b minus 2c, and that should balance out to 2 on the other side of the equation. This, you'll notice, is a single equation with two unknowns. It has an infinite number of solutions, and this is why we need our cosine term. On the left, excuse this mix-up for a moment there. On the right, you'll note that we have an absence of cosine terms, which we can think of as saying I'm adding 0 times cosine 2t to this equation. On the left, my two cosine terms come from the 2b and the 2c, so balancing out my equation says that that expression should equal 0. Now we have two equations and two unknowns, which should be a familiar situation for you from Algebra 2 or some other course in high school. We can solve it using elimination of variables or substitution. I'll add them together and get 4b equals 2, which leads to the solution b is 1/2. And plugging that in for b into the second equation and solving for c yields c equals negative 1/2 as well. Finally, combining all this information, plugging in the values for a, b, and c into my formula for yp of t, we obtain a particular solution as 1 plus 1/2 sine 2t minus 1/2 cosine 2t. In order to apply the fundamental theorem of Math 57 to obtain our general solution, we also need the solution to the complementary equation, which in this case would be yc prime plus 2yc equals 0. This is again that exponential equation from the first day of class, and it has solution ce to the negative 2t. If that's still a little uncomfortable to you, pause the video at this moment and make sure you can work that out for yourself using separation of variables. Once I have both pieces in play, I combine them using the fundamental theorem of Math 57 to write my general solution to the dE as yp of t plus yc of t, which in all its glorious detail says 1/2 sine 2t minus 1/2 cos 2t plus 1 plus c e to the negative 2t. And I think at this point you've probably done this PSI enough to know that you would plug in 0 for t at this stage and set the result equal to 0 to solve for the value c. And you should get c as negative 1/2, which leads to the final formula for the solution to the IVP. I wanted to conclude this video by comparing this analytic formula with what we saw in yesterday's lab in the graph. We recall that we earlier pointed out this short transient function at the beginning of our solution, and that transient function exactly corresponds to this decaying exponential, which goes to 0 pretty quickly as t goes to infinity. If we have a part of our solution that decays to 0, We call that the transient part of our solution. It doesn't really matter much for determining the long-term behavior. In contrast, the other part of our solution, which is an oscillating sinusoidal function, is what we call the steady state part of our solution. And that's what we see dominating the behavior of this black output as time continues on. We'll see the same type of phenomenon occur when we study RC circuits in tomorrow's class, so we'll look forward to seeing you then.